Okay, I think it's time to begin today's webinar. So hello again, everybody, and welcome to this Dekati webinar. Our topic today will be standardized and advanced engine exhaust measurements with Dekati eDiluter Pro system. And the contents will be the following. So first we will have a brief look at Dekati. What is the Dekati company and what do we do? And then as a background, we will discuss briefly why is the sample conditioning and dilution needed in engine exhaust measurements. After that, we will introduce our solution, our newest solution for sample conditioning and dilution, the eDiluter Pro. And after that, we will go through some of the engine exhaust measurement regulation, the emission regulation and regulatory setups. Then some examples of other engine exhaust research setups like non-compliant setups. And then at the end, we will have a couple of case examples. And I warmly welcome you throughout the webinar to add questions. There's the Q&A section in the Zoom that you can use. I have a couple of slots reserved, so I can have a look at those questions then, and also might point something out also in between those couple of question slides. All right. So Dekati has been developing and manufacturing fine particle measurement solutions for over 25 years now. Our background is in Tampere University of Technology Aerosol Physics Lab. We are located in Kangasala, Finland. And most of our sales goes through to export through our wide distribution network. And as mentioned on the slide, it is not only the measurement instruments that we produce, but also we are specialized in sample conditioning. So sample conditioning and dilution, even from very challenging sample conditions. Here's a quick look at our product range. And in today's webinar, the focus will mostly be on the Dekati eDiluter Pro. And Dekati instruments are being used in very wide range of measurement applications, as can be seen here. And today the focus will be on automotive exhaust measurements. So for a background, if we think about engine exhaust measurements and partially also particle measurements in general, why do we need sample conditioning and dilution? Well, here are some key points to answer that. So one point is obviously to dilute the sample in terms of reducing the particle concentration. Basically, all the measurement instruments for particles, at least most of them, have some sort of boundaries and minimum or maximum values that what is the particle concentration they can handle. And usually it is more problematic for particle number measurements than for particle mass measurements. Also, when we are measuring combustion-related aerosols, it is important often to reduce the sample temperature. Again, most of the instruments cannot handle hot samples, for example. Also, when measuring particles, it is not that straightforward that you just get some particles and then measure them, and then the results would always be comparable. You have to always take into account that Do you include the volatile particles or do you evaporate them, for example? And in most of the cases, at least the legislative cases, you want to evaporate the volatile species so that you are not measuring them. And I already mentioned the legislation, so regulations are also an important aspect, and we will look at those in a bit more detail soon. But they also require usually some specific sample conditioning and also dilution depending on the measurement and application. And another important aspect is that, well, obviously the legislation sets its boundaries on how you can do the sample conditioning and dilution. But even if you are doing non-legislative measurements, you still have to do it carefully, because you cannot just use some kind of way to reduce concentration just by randomly adding filtered air into the sample or having the sample cool down in some tubing or so on. So in order to get good results, repeatable results, and comparable to other results, you have to take into account that the concentration and temperature should be reduced in a controlled and traceable way, because the particles are quite tricky to sample and measure in many cases, and they go through various kinds of sample transformations when they are being transported in the sampling lines, for example. So the dilution should be done so that we avoid this unwanted sample transformation as much as possible. Also, we want to, in general, minimize particle losses, and also the amount of reduction we do to the concentration should be traceable, and we have to achieve a dilution factor that we know. If we don't, then we will never basically know what is the original concentration at the source, which is the thing we are interested in when we are measuring engine exhaust. At least that is the assumption. If we look at the eDiluter Pro and how does it work to cope with these challenges, is that it has a two-stage ejector dilution. First stage can be heated, and the second stage is at ambient temperature. And in general, when measuring combustion aerosols and diluting them, it is preferable to have the first dilution stage heated, so that we don't get condensation of the sample and thus the sample transformation. So when we do the first dilution with heated, clean dilution air, then we can reduce the vapor pressure and it won't condensate again. And then it is safe to do the cold dilution on the second stage. And also in this ejector dilution system, it is not, it has some enhancements, for example, compared to the Dekati diluter, the DI1000 diluter that has been widely used for combustion aerosols. So part of the dilution air goes to this small axial type of dilution before the actual ejector, and it also provides kind of sheath air flowing so that the ejector nozzle will not easily get clogged. Also, another important aspect is that in the eDiluter Pro, the inlet pressure is constantly monitored, and there are automatic pressure controllers within the unit to also tune the pressure upstream, the critical orifices that lead the air into the ejector, so that it won't change the dilution factor even the pressure fluctuates. I will show some results related to this later on. And the sample in let flow is in the range of 3 to 10 liters per minute, depending on the chosen dilution factor. So dilution factor is also adjustable, and outlet gives the possibility, the outlet flow, to sample with several measurement instruments. Also, there is the option for cases where you need only a low dilution factor. You can also sample from straight after the first dilution stage, from the outlet of the first dilution stage, and this can be used when you need low dilution factor, or you need to keep the sample hot, for example, for a heat seat filter holder or some other instrument, for example. So the nominal dilution factor range for the whole system is from 25 to 225, but with this solution, you can go even down to 5. Here are some more specifications. I won't spend this time to read them aloud for you, but I will point out the main features related to the specifications is that the dilution factor is adjustable, and you can adjust it in real time. If you see that the concentration is too low or too high, you can add it or reduce it online. And also the sample pressure range is wide. It's a bit different pressure range for each first stage dilution factor setting. So the first dilution stage dilution factor can be 5, 10, or 15, but these are the ultimate minimum and maximum values for that. And the dilution factor is automatically compensated for inlet pressure and ambient temperature. So that is taken into account in the unit. And maximum sample temperature 600 degrees. But we have a special 1200C version with a high temperature probe that can go up to 1200 degrees. Also, let's have a brief look at what is the construction. Well, actually, as you can see here, it is very portable. So it weighs only like 6.5 kilograms, and the dimensions aren't that huge either. So it's easy to move around into different measurement locations. Sample inlet is at this side, and the outlet ports by default there is 3 of them, and one port must always be left for exhaust use, but the other ports can be connected into measurement instruments. And if you want to measure with more than 2 instruments, you can of course add branching to these, so you can use as many instruments as you like, or at least as many as you can do with the flow provided. But the flow is quite high, so as you noticed, there is a small protective particulate filter here. So the pressurized dilution air goes in through this. Pressurized air should always be clean and dry in order not to mess with the instrument, but also not to mess with the results. We don't want to dilute with air that has particles in them. But this is to protect. This doesn't do the whole cleaning and drying. As you probably know, the cleaning and drying units are a bit larger than this, but this is just extra precaution. Here's the display and the control knob. So the instrument can be controlled by this control knob, or it can be also remotely controlled via commands through this USB connection. So this is the back side of the unit. You can connect 2 external heaters here, and they can also then be easily controlled using this eDiluter Pro. So you don't have to have a separate controller for each heater, for example, that you use. And there are a couple of thermocouple connectors as well. And it is quite easy and straightforward to disassemble for cleaning, for example, so you don't have to keep sending it into service each time it gets clogged. If you, for example, take very high concentrations or don't remember to put on the heating and condensate some sticky stuff into the unit. So it's very easy to disassemble the diluter package, so to speak. You can get it out and then disassemble it and just clean it in ultrasonic bath. And for disassembling, you can see our YouTube videos. Also, we have videos on how to start the measurement, so you can have a look and see the convenience. Some examples of accessories we can provide with the unit. So to make a complete solution, you can have all the needed components. The cleaning and drying units for the pressurized air, heated sampling lines are available, and this heated sampling line holder system is quite convenient, and it is included in the eDiluter Pro package, because you might know that these tend to get bent quite easily sometimes, and this keeps it firmly in place, at least at this side of the connection to the eDiluter. Heated probes, cyclone to cut off the coarse particles, cyclone heaters, and so on. I'll have a look if there are any questions at this point, and remind you to please do not hesitate if you have any comments or questions. At least I see none at this point, so I will move forward to the legislation. So here are some of the main vehicle emission regulations at the moment. The focus on the following slides will be on the UNECE regulations and this Nonroad ISO standard, which also both then relate to this GTR, which is the global technical regulation for the test procedures, which is quite well in line with these standards and regulations. And the way we look at the regulation is obviously mostly we focus on the test procedure, what the setup has to be, what requirements does it set to the instruments that we use. The US regulation, at least for the moment, they focus basically only on the PM, and these do not require any specific dilution solutions, as they don't have the particle number in them. So we will not focus on the US regulations now, but have a bit closer look at the regulatory test setup for these light and heavy duty vehicles, also that are then applicable to the Euro 5, Euro 6 emission measurements, and then the Nonroad standard ISO 8178. So in engine exhaust measurements especially for light duty vehicles, Euro 5, Euro 6, you probably are familiar with the CVS Tunnel. So one way to measure is to do it with full flow sampling via a CVS Tunnel solution. So this means that the complete exhaust gas flow from the vehicle is led to this large CVS tunnel where there's a quite high flow of air that is being filtrated before it enters the tunnel, and then after the sample has mixed in the CVS tunnel, there is a sampling nozzle that then collects the sample to the measurement setup. And in the measurement setup, it is specified that there is a cyclone to cut the largest particles away. Or recall correctly, it must be between 2.5 and 10 microns, the cutoff size in the cyclone. And then after that, you will have to have a volatile particle remover. So the volatile particle remover system in the regulation consists of particle number diluters, and also it mentions the evaporation tube. So the idea is that it reduces the concentration in a two-stage dilution and also evaporates the volatile species. After that, the diluted sample goes to the particle number counter, which is a condensation particle counter, a CPC, and then the excess sample is let out. And the dilution media is clean particle-free dry air normally. And the eDiluter Pro is an instrument that can be used as a VPR for these regulatory measurements. It fulfills all the requirements for these standards, which we'll also have a look later on and show some results of those measurements. Then just briefly to see the particle mass measurement setup. As mentioned, this doesn't require a dilution. It is quite straightforward: cyclone, filter holder, flow controller, and a pump. So it's a regular weighing procedure for the PM. Then another option on how the particle number and mass measurements according to these UNESA regulation can be done is to have this partial flow sampling. So in this case, the nozzle takes the sample from raw engine exhaust straight into the following system, and the system in this case is a partial flow dilution tunnel. So actually it takes a constant proportion of this raw exhaust continuously. So the flow controllers are very, very important in this first part of the system, and also for the total flow. So the total raw engine exhaust flow is being measured so that the proportion of the inlet flow going through this nozzle is always, for example, like 2% of the engine exhaust going out. So, and it is then adjusted by adjusting this flow that gives the dilution air into this dilution tunnel, and the amount of dilution air that is being pushed here, and then the pump that pulls the full flow then determines the amount that gets pulled from the raw exhaust. But if we look more carefully at the actual particle number measurement, the solution is basically identical. So we have the volatile particle remover here, and then the CPC here. One difference is that in this system you can use one cyclone and then spread the sample for PM and PM measurements with just one cyclone. Also this is this partial flow method is, at least for the large non-road vehicles, the more common one than the CVS solution. So, which then applies to this standard. This is for the non-road vehicles, and for those, CVS or partial flow dilution systems are okay for particle number and particle mass. So very similar to the ones that are okay for the in the UNECE or according to the UNECE regulation. But in the addition, it allows you to do direct tailpipe measurements for particle number. So this is a very convenient option in many sense, because you need a lot less setting up and instrumentation, basically. Because what direct tailpipe measurement can, for example, look is this. So you have a tailpipe, then you have a probe going straight into the tailpipe, heated sampling line, volatile particle remover, for example, eDiluter Pro, and then the particle number counter downstream. So it is very simple compared to the complex setups we saw here. So to sum up the regulation and how they are related to the eDiluter Pro. So eDiluter Pro is compliant volatile particle remover for these Euro 5, Euro 6 type of measurements according to the UNECE regulation, and also then for the non-road vehicles particle number determination. And not only we have tested this thoroughly at Dekati, but obviously we have also now done certified calibration tests at Ricardo UK. And if we look at the future of vehicle emission legislation, obviously we cannot be sure what the next emission legislation round will look like, but we are being active in this sense and keeping updated on the future prospects and what is being discussed. So looking at the situation at the moment, the overall trend seems to be that the legislation is going a bit towards performance-based rather than technology or characteristics-based, which in our opinion is a good and rational way to go forward. So instead of just choosing some technology and going with that, the legislative measures are being looked at more like what must the solution provide and at what accuracy. So not to lock out technologies, just to make sure that the requirements are for the performance are put well into place. Also, probably you have heard this has been discussed for a long time already, but the lower cut point of particle number measurements is planned to go down to 10 nanometers instead of the current 23 nanometers. And the latest information is that the catalytic stripper in the volatile particle remover, the catalytically active component, seems that it will not be mandatory, but as a recommendation only. But also it is possible with our solutions to add the catalytic stripper if necessary or if needed. But basically, if we look at the volatile evaporation, it doesn't make a difference. I will show some results later on. And also it's moving into the direction that direct tailpipe measurement, as I showed you in the previous slides, will be in the future probably allowed for particle number measurements also in other regulation than the ISO 8178. it still requires you to measure the exhaust flow, and probably will start with heavy duty regulation first and then apply to light duty. But for eDiluter Pro type of solutions, it is a good thing, because with that one you can make the direct tailpipe measurement quite conveniently. So I noticed one question at this point. I can have a look at it quickly. Thank you for the question. What is the minimum and maximum pressurized air consumption in liters per minute? Let's have a look. I have it here. So the absolute maximum, which depends a bit on the sample pressure conditions, and obviously also then the dilution factor, absolute maximum is 200 liters per minute and 7 bars absolute pressure. But this is kind of a worst case scenario regarding the sample pressure and the dilution factor. So with a normal sample inlet, like ambient pressures, and in the dilution factor range, it is closer to 5 bar absolute, 120 liters per minute is the typical one. Right, moving on to the non-compliant setup, some examples of those. So obviously those regulatory measurements, well, they are mandatory, but also done very widely. But if we look at the research and development and scientific research, obviously other type of studies are also widely done to engine exhaust emissions. So here are some examples of those kind of measurement setups that can be provided with the Dekati instruments. So if we look at pre-after treatment directly from the tailpipe, or depending on the engine and vehicle, it might not be the tailpipe, but at a pre-after treatment sampling point, it is possible to just use the eDiluter Pro with, for example, a high resolution LP Plus that gives you the size distribution in real time in 1 Hertz or even up to 10 Hertz. If it's a type of an engine and a location that the overpressure is very high, it can still be sampled using the DEED 300 in combination with these instruments. So basically, let's say if it's over 1 bar of overpressure, then you will need some extra, but also, as shown, the eDiluter Pro can withstand some overpressure easily. If we look at post-after treatment, for example, a post DPF, a diesel particulate filter, as you know, if a DPF is working as it should, it is very efficient of removing the particles. So in those cases, the sample is quite clean and might be also almost particle free compared to the for example direct injection gasoline engine. So in many cases like this, the high temperature LP Plus is quite a unique and a good measurement solution, because it allows you to sample without any dilution, because you can heat the impactor and then pull the heated sample straight into the impactor and measure it in real time. If you are unfamiliar with the LP Plus, the electrical low pressure impactor, I recommend you to check out our website or our YouTube channel, where we have content either in shorter format, a short LP Plus video, or a longer webinar video showing the features of the LP Plus. Unfortunately, this 1 hour is not enough for me to get into the details of high temperature LP Plus or high resolution LP Plus. And obviously, these both setups then also work if one wants to do measurements from CVS or partial flow dilution systems for these non-compliant size distribution measurements, for example. Okay, seems that there are no new questions at this point, so let's go into the last phase of the webinar. So let's have a look at then the eDiluter Pro. Why does it comply with the regulation, and what are the critical aspects on what is important when you look at the performance of a dilution system? First, this dilution factor stability and accuracy is to have a look at the dilution factor accuracy with gas measurements and also the stability in evolving pressure conditions. Solid particle penetration and volatile particle removal efficiency are then related to the, well, on the other hand, the actual solid particle penetration, but these are both also then requirements in the legislation that I showed you a moment ago. So we had this type of measurements, gas measurements, to have a look at the dilution factor stability under fluctuating inlet pressure conditions. So we used a trace gas, and then we were able to control the inlet pressure. So here you can see the inlet pressure is shown on the blue line. So the inlet pressure was intentionally fluctuated throughout the measurement, and the dilution ratio, the dilution factor, is on the green line then, and the set point is the black line. So obviously when we set it on the instrument, it goes as a step function, but because there is some tubing, there is a small delay after the dilution. Also the sample represents the new dilution factor. Red line presents the concentration of the CO2. So as we can see, the green line, which is the dilution factor, does not start to fluctuate, even though the dilution, the inlet pressure is constantly changing quite noticeably in the range of 900 millibars to about 1,100, 1,200 millibars. Absolute. In here we can notice that with the highest dilution factor, we start to see minor inaccuracy, because also the dilution air has some CO2 in it, so the accuracy starts to become a bit weaker here. So it is not a factor of the inlet pressure changing, it is the CO2 concentration. And next, let's have a look at the solid particle penetration. So in the regulation for engine emission measurements, there are requirements on how much of the solid particles penetrate through the system. And for now, it looks at the sizes of 30 nanometers, 50 nanometers, and 100 nanometers in electrical mobility diameter. So the penetration of 100 nanometer particles is compared basically to the penetration of 50 and 30 nanometer particles, and the difference cannot be too large. we did all of these measurements with the whole sampling setup. So not only the eDiluter Pro, but also has the includes then the losses of the heated sampling line, 1.5 meters. In this test, monodisperse salt particles are being used, and we tested it with different dilution factor settings at ambient temperature and also the at 300 degrees Celsius. Here is the sampling setup. So DMA is being used in order to just feed and select the electrical mobility size particles that we want. So 30, 50, and 100 nanometers. And then we measure the particle number concentration before and after the system. So here are the results of checks done at 20 degrees Celsius. These results are from our lab shown here. So the accepted range in regulation is shown as these red marks. It is a bit bit special, this way to visualize the solid particle penetration, but it is the way that it is done in the regulation. So it compares the particle concentration reduction factor against the particle concentration reduction factor at 100 nanometers. So this shows that there are a little bit, which is always basically the case, a little bit more losses on the 30 and 50 nanometer particles compared to the 100 nanometer, but they are well within the range of regulation. And we also measured, in this case, the 15 nanometer particles. They are not in the legislation yet, but probably will be when it goes down to 10. And we expect it to be well within regulation for that as well, because the reading, the requirement, the maximum range in regulation will probably be at around 2 or even 2.2 or something like that. So we're very happy about these results, and again, the same results here for 300 degrees Celsius. And these tests are also done at Ricardo, UK, and they confirmed the same results. And well, obviously not the same results, but they also had the numbers within the accepted range of regulation. And the last tests here related to these regulations, volatile particle removal efficiency. So according to the regulation, the volatile particle remover must remove volatile particles efficiently. So it has to remove over 99% of 30 nanometer tetra-contained particles when the inlet concentration is over 10,000 particles per cubic centimeter. Okay, so in this case, the setup is similar, but we use different particles, tetra-contained particles, which are volatile. Then a DMI classifies only the 30 nanometer mobility size particles. And again, we measure the particle number before and after the eDiluter Pro. And in this case, we wanted to only look at the eDiluter Pro. So obviously some volatilization would happen if we use the heated sampling line, but we measured without it because we wanted to see that the eDiluter Pro would cope and be able to volatilize those particles also by itself. And here are the results. So here is the on the y-axis, the tetra-contained penetration. So the legislation requires the penetration to be under 1%. So it needs to volatilize over 99% of the tetracontained particles. And we did the measurements with several different dilution factors shown here on the x-axis, and did the measurements with several dilution temperatures. So that's why there are these different colored dots in the graph. As we can see here, with 20 degrees and 100 degrees Celsius, the tetracontained doesn't start to evaporate basically at all. With 150 degrees, we get some evaporation, 200 degrees, bit more. 250 degrees Celsius, we are quite close. Only one measurement result is a bit over the range, but when we put the dilution temperature to 300 degrees Celsius, we pass clearly, and the upper limit for the temperature is 400 degrees Celsius. So that is the maximum temperature you can set in the eDiluter Pro. So there is also room to add it, but it clearly passed with 300 degrees. Also, these tests have been done at Ricardo. Okay, before I go into this, I could have a look at the questions. At the end, I will have a couple of measurement examples to end the webinar. Here's a question: what is an approximate budget cost for a basic unit which will measure 25 and 10 micron particles? Thank you for the question. This is actually these are quite large particles. So if we talk about engine exhaust, these are in the out of their scope and out of the scope of the eDiluter and eDiluter Pro normal use. So for over 10 micron particles, I wouldn't recommend the eDiluter Pro system. It's more for the PM10 area, definitely. So I would recommend a different kind of approach probably for those particles. They need a different technology to cope with the loss mechanisms involved with those. The losses become very high in those particle sizes by different phenomena. Yeah, we can of course advise you. So please contact us, and we can advise you with the different type of solutions for those very large particles. Okay. Next question: what is the minimum and maximum pressure of sample inlet? And also, do we need a pump to deliver the sample to the eDiluter? Good questions. Minimum and maximum pressure of the sample inlet, as shown in the spec sheet, are, I will show them again briefly here. So the absolute minimum and maximum values are 850 millibars absolute, 2200 millibars absolute, but this depends a bit on or depends on what is the first stage dilution factor setting. But this is the area that is possible to reach with the correct dilution factors. But with basically all dilution factors, you can reach easily like 900 to 1300 millibar, independent of the dilution factor. And the question about the pump, no, you don't need the pump to deliver the sample to the eDiluter. So with the Ejector dilution system, you only need the pressurized air going into the unit. So you need to push the air into the unit so that it goes via these dilution air inlets into the Ejector diluter. So as it flows through, besides the ejector nozzle, the flow here provides the Venturi effect, so that the high flow going next to the ejector nozzle pulls the sample in via the inlet. So the suction is created by the pressurized air being pushed into the system. So even without any instrument or connected into this outlet, you will get sample flowing out of these. Obviously, then you will need, with the measurement instrument, normally some kind of a pump to pull the flow from this exhaust into the correct flow into the unit that you want to use. But no pump needed to push the sample or pull the sample in. It's caused by the pressurized air. And okay, yeah, and added to the first question. Yeah, okay. Then there is a question about the dilution factor settings. If I want to dilute 1:75, is it better to set up 1:15 at the first stage and 1:5 at the second, or the other way round, or there is no significant difference? Well, both ways do work. It then depends also a bit on the sample or the dilution temperature, because one point also is that if you use very hot dilution air, for example, use it at the maximum value of 1:400, then you and use the high dilution factor here, 1:15, and only 1:5 here. Obviously, the sample still at the outlet will be close to ambient, but it will be in higher temperature than if you do it the other way around, like having only 5 dilution factor here and most of dilution or more of the dilution coming from the ambient air. So at least it is then it will affect a little bit then the exhaust or the outlet temperature of the sample. But I wouldn't say that there is no drastic difference in most cases. Okay, thanks. Those are the questions for now. And let's have a look at the last slides concerning some couple of example cases. So here's one example case. We did at Dekati some measurements for a Euro 6 diesel passenger vehicle, but it had a broken DPF. Actually, it's one vehicle of the people who work at Dekati. Actually, it doesn't have that car anymore, but when we tested some measurements and did some demo measurements, we actually in those noticed that the DPF is broken because it was the particle numbers were way too high. But after that, we did some more measurements to also it provided us the opportunity to test our instruments with a vehicle like that. So we had a straight from tailpipe this kind of a non-compliant setup because we wanted to look at the size distribution data too. So we had one setup that had a perforated sampling probe, heated sampling line, and a high temperature LP+. Heated sampling line was heated to 200 degrees Celsius, and the high temperature LP+ impactor to its maximum value of 180 degrees. And the other setup had the same sampling line, sampling probe, but here we did the 2-stage dilution with eDiluter Pro with a total dilution factor of 100, and then the ambient temperature sample went into the high resolution LP, so it didn't have the heated impactor. So we wanted to compare the results for these two setups and see how well they match. Both of the instruments had sintered metal collection plates on them. Just a couple of photos. Sorry for the not so good quality, but these were what I was able to find from these measurements. So here are the probes, and you can see that the heated sampling lines, one of them goes into the heated impactor in the second picture, and the other one goes into the eDiluter Pro, where the black sampling line goes into the LP Plus, which is located inconveniently behind that door. So here are the results of those measurements. So on the orange line, you can see the high temperature LP Plus results. So without dilution, straight into the heated LP Plus, and the other one, the more yellow colored one, is the one that was diluted with the eDiluter Pro. And here you can see results for both cold start and then another measurement done when my colleague had driven the car for some time and warped the engine up, and then the emissions were lower, but still much higher than what we would have seen if the DPF would have been working as it should. But we were very happy about these results. They match very well and shows that in this case the dilution did not change the size distribution, and also the dilution factor seemed to be accurate, because obviously these results have for the diluted sample have been corrected with the dilution factor, and after that they show the same range of concentration. And here's another example of some non-road vehicle measurements we did on a mining vehicle, a Sandvik mining truck. And in this setup, we had heated sampling line, eDiluter Pro, and the LP Plus. And here is the test protocol they use for these mining vehicles. They don't have any, at least in most places, like a own dyno for these mining trucks. So what they do is they have this kind of test protocol where they have the engine running in low idle, then they put the brakes on and push the throttle against the brakes, have the high idle, then again to the low idle, then some shorter stalls against the brake, again one longer stall, and at the end another high idle phase. So here are some pictures of the setup. Again, we had the probe inserted into the tailpipe. It was led to the eDiluter Pro and then onto the LP Plus. You can also see that the dilution air is connected into the eDiluter, and there's a cleaning and drying unit in between. And here are some results of those measurements. So we got on the left-hand side the particle number size distributions from the measurements, and particle mass size distributions on the right-hand side. And on the graphs in the middle, there are the concentrations data second by second throughout the cycle also. And what is quite surprising about this, that even though this test protocol is only done by the driver doing the throttle and the stalls against the brakes, the peaks are quite comparable still in these 5 stall periods and so on. And the LP Plus size range goes up to 10 microns, but these graphs are limited to 1 micron, the PM1 area, because actually there weren't any particles in the 1 to 10 micron area, so they wanted to focus on this PM1 area. Okay, time's up, and luckily also the slides are so didn't go into extra time. I'll just quickly look at the questions. There are no new questions now, so I want to thank you everyone very much for attending the webinar, and just a short reminder at the end, if you have any remaining questions or wanna hear more about these solutions, don't hesitate to contact us, sales@dekati.fi, and these webinar recordings and also other nice Dekati content is available in our YouTube channel, and you can also follow us on Twitter. Yeah, thank you very much, everyone, and have a good rest of the week. Bye bye.